Now we're ready for problem 4.2, and this problem more closely resembles the chutes and ladders problems. You should probably watch both of the videos before you start kind of tackling the homework. But okay, so for this problem, what are we going to do? Well, we're going to roll a dice, and we're going to keep track of what the highest number is. So let's just do this for ourselves in an experiment. By the way, you should always have a starting state. And for us, the starting state is going to be 1, because if you haven't rolled a dice, then I think it makes sense to say that the highest number you've rolled is a 1, because you can't get anything lower than 1. So 1 is a good starting state. And then I rolled a 4. So state number 2 is 4. What about state number 3? I rolled a 3, but notice it says I keep track of my highest roll. My highest roll is still a 4. Right? Now I got a 5. Oh, my highest roll is now a 5. Now I've got a 3. So it's my highest roll so far is still a 5, because I'm just tracking what is the highest roll I've had so far into the game. 1, that doesn't affect it. My highest roll is still a 5. Still a 5. Eventually. And what you'll see is that this is going to keep going until I finally get a 6. Wow, it's going forever, isn't it? Ah, there we go. And now I got a 6. And then you can see it doesn't matter what I roll, because everything after this point is going to be 6, 6, 6, 6, 6, 6, 6, 6. So what you can see when I played this game is that you rolled your dice, and if you get something higher than your current highest score, you increase it to that. And if you get something lower than your current highest score, you don't. You stay where you were. Okay. So this is not a very fun game, I guess, to play, but it's an interesting thing to think about probability-wise. So let's try to build ourselves a transition matrix. And you'll remember from the previous problem, our transition matrix is just our matrix where we put all of our froms on the top, and we put all of our twos over here on the right. So notice we could start with the state where we're in state 1, 2, 3, 4, 5, and 6, and then we could end up in state 1, 2, 3, 4, 5, or 6. So our matrix is going to be a 6 by 6 matrix. We could start in any of those and end in any of those. Well, let's just analyze each one at a time. If we're in state 1, so if the highest thing we've rolled before is 1, notice that whatever we roll, if we roll 1, 2, 3, 4, 5, or 6, that's going to be our number from then on. So each number here is going to be 1/6. So I have a 1/6 chance of going to every state between 1 and 6 from the number 1. The number 2, however, there's no chance that I can end up with a 1, because if you start in state 2, if you roll a 1, you stay in state 2 because your values never go down. So this has to be a 0, right? So once I had a 4, I couldn't go back to a 3 or 2. I had to stay there because your numbers only get larger as we play the game. Now, the probability of staying in state 2 is actually bigger than 1/6, because if I roll a 1 or a 2, then I'm going to be in this square. So this one is 2/6 or a third. Okay. And now, the only way to get to state 3 is to roll a 3. And the only way I get here is to roll a 4, roll a 5, and roll a 6. So I've got a 1/6 chance of rolling 3, 4, 5, or 6. I've got a 2/6 chance of rolling either a 1 or a 2. Okay. Maybe at this point you're starting to catch on. When you're in state 3, you can't get a 1 or a 2 because you can't go backwards. There's a 3 out of 6 chance, or 1/2, 3 out of 6 chance that you end up in state 3. So if you're in state 3, there's a 3 out of 6 chance you stay there because you didn't roll anything higher than 3. And then the rest of them are 1 out of 6. All right, great. And now we can see our pattern, so I'm just going to finish this off. 0, 0, 0, 0, 5 out of 6, and 1 out of 6. So we saw that, right? Once we hit our 5, there was a 5/6 chance we stayed in 5. So it was really likely we stayed at 5. It was hard to go backwards at that point. And now 6, what happens when you hit state 6? When you hit state 6, you're guaranteed to be a 6. So you've got 6 out of 6, or 1 right here. So this is our transition matrix. So really, the question is, once you have a transition matrix, how do you how do you make kind of different conclusions? Well, what I'm going to do is I'm going to put that transition matrix into my calculator. Guess what? I already did it because I wanted to save you all the pain of watching me type this in the calculator. So, so there's my transition matrix. I've typed it all in the calculator. And then what we're going to do is we're now going to look at what happens 3 turns later. So to do 3 turns later, I just need to take that matrix that I put, which I have it in A, and then I just need to cube it. So I'll raise it to the 3rd power and look, and wow, our matrix is crazy. It's got all sorts of decimals. I have to scroll over to see things, and you all like it when this happens. And by the way, when you get to your homework and you have a 12 by 12 matrix, I'm really sorry. It's gonna be really big. I guess you could, if you wanted, you could. There are lots of places on the internet that multiply matrices for you, so maybe you could do it there and have a bigger screen to work with. That's up to you. Okay, so here's our calculator, here's our matrix. So if you look, this first row, what does this first row tell it? It says if you start with 1, this is the probability of ending in all those. So if you roll it 3 times, there's only a 0.4% probability that you end up with a 1, because that means there's only a 0.4% chance you rolled a 1 3 times in a row. There's only a 3% chance you end up with a 2, and look, there's a 42% chance that you end up with a 6. So for part B, you find that your probability is 42% chance that you've had a 6 after 3 rolls. Notice that definitely wasn't what we had. Now, what's the long-term behavior of this process? Well, you might notice, you might be able to guess, this game ends the exact same way every single time we play it. It always ends on a 6. And once it ends on a 6, it stays there. So what would that look like for our matrix if we were to raise it to a really big power? Let's try raising it to the 300th power. This might break our calculator. Let's just give it a go. Yeah, it didn't like it. Okay. It liked 100 earlier. Will it do 100? Oh, it's working on it. There we go. And now notice we've got to the -78th, -48th, -30th. So these numbers are all basically zero. And what's our last number? Our last number is basically 1. So the long-term behavior of the matrix is that the matrix hits 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 1. So that's kind of what we end up hitting every single time. And what does this mean? This means that in the long run, you end up at a 6 and you stay at a 6. And notice this is how we're going to think of our Chutes and Ladders game, because when you play Chutes and Ladders, you end up on the finish, you never leave. You just stay there once you hit the finish. So there you go. Okay, so the long-term behavior is it stays in a 6. This is what we call an absorbing matrix. So this matrix is called absorbing because it's some sort of behavior where we have our states, but there's some states that you never leave. And so the long-term behavior is that some states end up being funneled towards and some states end up not being part of the final long-term behavior. This is versus a regular matrix. A regular transition matrix was like the one we saw earlier with the Monopoly problem, where over time every square has a chance of being hit. So you continue to hit every square as the game goes on forever, versus absorbing, where some squares or square absorbs all of the turns and some squares end up basically being removed from the calculation. Okay, so you're ready to start your Chutes and Ladders. What do we need to do the Chutes and Ladders problem? You'll need a 12 by 12. I would start on 1, so I would think of your first term as just like this problem, as starting on square 1 at the very beginning. You'll actually notice there are some squares you can never end on. So for example, you can never end on 2, because anytime you're on 2, you get shot straight up to 10. So, so you could leave 2 out of your problem altogether, or you could just have a row and column of zeros on that 2 slot, because you can't actually end up at 2, and similar with 4. Another decision you'll have to make is there are really 2 ways to play Chutes and Ladders. One way is, suppose you're on square 10 and you roll a 5. If you roll a 5, one option is to say you stay on square 10 and don't move. The other option is to say you go automatically to the finish if you roll a 5. And you'll have to make that rule for yourself. I don't care which rule you choose. I know when I play with small children, if they roll a number bigger than the finish, we let them win, because otherwise they get very sad. But you can choose either one of those rules, and so that means your answers will vary just a little bit. All right, so again, good luck. Find yourself some classmates, work together on these problems, and please come see me in study hall hours, and we will get them. So with this assignment, I would like you to do these 2 application problems and turn them in to me as soon as you get them done. So good luck, and I'll see you in study hall.